Thank you very much for the very nice invitation. It's really great to be here. I'm really looking forward for the rest of today and also tomorrow. Sorry, is there a problem with the screen? Me and Michael and Theo already set up the basics for me, so my job is easier now. As Michael just mentioned, I'll be talking about graphs. So this one will be introductory lecture on graphs. And you've already seen some examples of graphs in the earlier lectures. So graphs are really ubiquitous in real world, in many domains. Starting from nanoscales like molecules, where we have atoms and bonds between them. They are naturally characterized as systems of relations and interactions. To miniscales like interactomes, or all the way up to social networks or information about the world. So we can really model lots of real-world phenomena using graphs. And why do we care about graphs? Well, there are some simple arguments. First of all, it's a very simple mathematical abstraction to model systems of relations of interactions. There is a very well-developed theory of graphs and many successful applications already ranging from chemistry all the way to pure maths. And it's widely argued that in many ways graphs are the main modality of data that we receive from nature, and graph representation learning is likely on the road to artificial general intelligence. And there's this nice quote from Jay Forrester, which also supports these arguments from a more philosophical and cognitive science point of view. He basically states that the image of the world around us, which we carry in our head, is just a model. Nobody in his head imagines all the world, government or country. He has only selected concepts and relationships between them and uses those to represent the real system. And the origins of graph theory can be dated all the way back to Euler, to this famous bridges of Königsberg problem. And as Michael already mentioned in the previous lecture, the name graph was coined for the first time by James Sylvester in the context of biochemistry, in a chemical context. Good, so this was just like a general introduction. You've already seen some of these things in the previous lecture, so I don't want to spend too much time on this. Let's talk about machine learning on graphs, right? So we think graphs are important. They appear in real-world systems. It gives us a very nice abstraction, and we would like to be able to do machine learning on such data, graph structured data. What type of machine learning? Well, we can do pretty much any type of machine learning on graphs, right? So we can, for example, take a regression and apply it on graph level tasks. So this would be graph regression task. For example, the input could be a molecule, right? And we may be studying a drug discovery context, and it may be important to predict the solubility of this molecule, right? And the solubility prediction is a graph regression task. Yeah, we look at the properties of this molecule implicitly and try to predict whether this molecule will be water soluble. Good. Another example, the task doesn't have to be on graph level, of course. It can also be on the components of the graph. For example, it can be a task on nodes. In this case, I have an example of node classification. Imagine we have some kind of social network where we have entities such as people or organizations, right? And they interact with each other. So the interactions are modeled as edges between the entities. We might be interested, for example, whether there is a malicious user in a social network, and this would be a classification task, right? So for any user, in this case, it will be a node. We aim to predict a Boolean value. Is this a spammer or not? Right, this would be a node classification task. Or we may look at pairs of nodes in a graph and try to predict link level properties. So one example of this would be, again, maybe in the social network context. So given a pair of entities which are not yet connected to each other, we would like to predict the likelihood of these entities having a link between one another, right? So this link would represent, in this context, which other user is this user likely to follow, for example, right? This could be a prediction task. Good. So again, we talk about invariant and equivariant tasks. So if it's a graph level task, we will essentially be talking about invariant predictions. So the example that I gave earlier about solubility, water solubility of a molecule is a graph level task. So we are speaking of invariant predictions here. And the other example where we are trying to identify whether a node represents a spammer user is an equivariant task. It's a node level task. Good. A very general overview. We will speak of graph neural networks as parametric graph functions. The typical setup that we will be referring at will be as shown here. So we will assume some input graph, usually equipped with features. In most of the lectures, we will just assume that there are some node features available. And we have a graph neural network. It's just a parametric function that's parameterized with some neural networks that just maps this input to some output. And the general pipeline looks like this. So we have an input graph, and this parametric function is a graph neural network. And all that we are trying to do pretty much boils down to this picture, because we are trying to learn representations, vector representations that correspond to the input graph or the nodes of the graph, and so on and so forth. So if you're interested, for example, in a node-wise task, what we would like to do is, after passing this graph through the graph neural network, is to learn vector representations that correspond to the nodes of the graph. Yeah, and this we will usually denote by, so for a node I, we will write Zi to represent the vector representation that's outputted by the graph neural network. Good. So we have these node representations. What if we have a graph level task? What do we do? Well, what we do is we kind of define a new function that pulls together all these node level representations to yield a graph level, a single vector that represents the whole graph. So what could this be? It could be a summation, for example, right? So we are given a set of like all these node embeddings. We just take the sum of them as the representation of the graph. Now we have one vector that kind of characterizes the graph. And then we can feed this vector to any machine learning classifier, for example. If we are interested in doing classification, we can just input this vector to a classifier, say an MLP, and get the result. And very similar idea for edge-wise predictions or link predictions. Now we have to look at pairs of nodes, right? And then we define an appropriate decoder or some scoring function that takes these pairs of nodes and produces a value for us. And that will be essentially representing the likelihood of having an edge, for example, between the two nodes. Okay? So what is this general picture telling us? So we are taking an input graph, and graph neural network is helping us to generate vector representations out of this graph. These could be node level vectors, graph level vectors, and so on and so forth. And why do we expect this to work? Well, the idea is that nodes that have similar characteristics, both structurally and feature-wise, the hope is that they will end up having similar vector representations, right? So when we're interested in making a node classification, for example, nodes that have similar properties will end up having similar, end up in close proximity to one another in the embedding space, so they will become more likely to be classified in the same way, as opposed to nodes that don't share similar characteristics, right? So this is the intuition. Good. An important discussion before we get into details is different kinds of regimes that graph neural networks can apply to. One regime is the transductive regime. This was more, let's say, the outdated regime, where we assume that we make only predictions on the training graph, right? So, for example, we may be interested in predicting some node-level properties, node-level regression, node-level classification. And the strong assumption here is that we have access to the whole graph. We may not know, of course, for some nodes, the classes, the labels, they may be missing, so it's still a meaningful prediction, right? But we observe the nodes at training time. So no new nodes are allowed and no new graphs are allowed at test time. The more interesting setup, of course, is the inductive setup where graph neural networks shine. Here we can observe both new nodes and completely new graphs, essentially. So we could be training on a graph that's shown on the left-hand side on this slide and predicting on the graph that's shown on the rightmost side, which are completely different graphs. Okay. Maybe let's take a step back and cover the basics. With a graph, we will refer to this pair, which consists of a node set and an edge set. This is a standard definition. I'm pretty sure you encountered this before. So we'll be referring to node sets and edge sets, and we will write the standard notation here, UV in E, denoting that there is an edge between U and V, and this is sometimes abbreviated as U tilde V. Good. And edges, notice that in general can be directed. They might have weights and all these things. And in these cases, we might have U connected to, there might be an edge from U to V, but not from V to U necessarily. But in most of these lectures, we will also be focusing on undirected graphs. In those cases, because the edges are undirected, we will just write UV, which represents both directions then. Good. As I said earlier, we will be also using featured graphs, so we will assume that the graphs are node attributed, right? So for every node, let's say node U, there will be a feature vector, which is denoted by XU, that represents some domain information about this node, right? This is what we will assume. And sometimes we will also use scalar edge weights, and that's denoted by WUV. Good, so this we have seen before also, thanks to Theo's lecture. How do we represent graphs? Because eventually we would like to, these are complex objects, right? So we want to represent them in some way in the machines to be able to do machine learning on top of graphs. Okay, we start with the feature matrix. Let's say I have this graph shown on the right-hand side, which consists of 11 nodes, right? For each node, I have a feature vector, right? So in this case, I have 11 feature vectors. Each of them is of dimensionality 4. I mean, typically it's n by d. In this case, it's 11 by 4, right? So 11 features of 4 dimensions. That's fine. And I assume that the nodes are indexed from 1 to 11, right? Just for ease of convention. Good. So the feature that corresponds to the first node is x1, and so on and so forth. Now what remains is to represent the graph. So now we have the features. We just stack them into a matrix. That's my feature matrix. Now I have to somehow represent the incidence relationship in the graph, so the edges, right? And this I can do conveniently using an adjacency matrix, also indexed in the same way. So I take 11 by 11, n by n matrix in this case. And what it represents is pretty obvious. So I put 1 into the entry ij, if and only if there is an edge between ij in the original graph, right? Otherwise, I put a 0. Right, this is the representation that I'm sticking to. And in this illustration, you can see the colored parts are 1s and the white parts are 0s, effectively representing the topology of the graph. So we have 2 components, right? So the adjacency, that represents the topology of the graph, the structure of the graph, and the feature matrix that essentially encodes all the node features. Now, if you put these together, I have all the information that I need. So I can do machine learning on this pair AX directly, right? Now, one problem though is that also the other speakers have been touching on is that the ordering is completely arbitrary here. I just picked some ordering, right? It looked like natural because I just enumerated from 1 to 11 and then also use the same indexing in the adjacency matrix. But this ordering doesn't mean anything for the graph itself, right? Like I could have picked a different ordering, different way of indexing the adjacency, which means what? Which means that I have many different ways of representing the same graph. Essentially n factorial different ways of representing the same graph, right? There is no canonical adjacency representation of the graph. And this is not, adjacency matrix is not the one to blame here. Clearly, graphs are combinatorial objects, and they are hard to deal with in this sense. And this will cause us some trouble later on. Good. Let's remember what Michael explained in the previous lecture. So we were discussing sets, right? Machine learning on sets and deep sets. What we wanted is when we have same sets, right? When we're learning a function over same sets, their outputs should coincide. So we want it to be invariant, right? In this sense. What we want in the context of graph neural networks and in the context of graphs is essentially the same. So we are learning functions over graphs, let's say, right? If you're learning over functions of graphs, we want these functions to be permutation invariant. Yeah. So if we are dealing with same objects, if the graphs are the same, there is no reason to have a different output, right? The output should be the same. This is permutation invariance, and if you're interested in node level properties, then the corresponding notion is permutation equivariance. So to give you an example, so imagine I do a prediction on x comma a, right? This is the original feature matrix and original adjacency matrix. That's ordered where we assume some order that's shown on the right-hand side of this slide. And I have the modified one. So I apply a permutation matrix on the features, and I consistently permute also the entries of the adjacency, right, to reflect this change. And I apply my function on this. The result should be the same. So if I just change the order of these nodes, the answer should not change. Yeah, this is permutation invariance. And why is that so? Because there is no order over the nodes of the graph, right? And so my prediction should be order invariant. And this order invariant on node level is reflected by permutation equivariance, because what do I expect? So I'm making a prediction, a node-wise prediction, right? So for each node, I'm outputting a vector. Now, what happens if I just permute the order of nodes? Well, then I have to consistently permute the entries of the vector, right? This is what I need to do. And this is essentially permutation equivariance. So thinking of in analogy to deep sets, well, remember we had this permutation equivalent layers with some nonlinearities in between, and then a permutation invariant layer at the end. We have a very, very similar structure on graphs. The difference is that it's getting a bit more complex because we are not dealing with a set now, right? We are dealing with graphs. So if I'm making a prediction on a node, the way graph neural networks work is more like a local function where I'm applying permutation equivalent layers on a node, which is optionally followed by a permutation invariant layer. But what I'm doing is I'm essentially applying this function over the node itself plus the features of its neighbors, right? So what I'm effectively doing is I'm taking the neighborhood of this node, the features of those neighbors, throw them into a multiset, and applying this function on those. So this is the connection to deep sets. So in this context, we are not dealing with sets anymore, but multisets, which we obtain from the neighborhood of the node. And why multisets? Because two neighboring nodes might have same features, right? So the features might repeat, and I would like to be able to represent multiplicity in these multisets. Right, let's have a closer look. Let's say I would like to compute a representation for the node I, and assume that the features look like this. So I have I's own feature is this red feature. It has two blue neighbors, one green neighbor, one purple neighbor, and one yellow neighbor, right? How do the multiset of neighboring features look like? Well, they look like shown on the left-hand side. The order here doesn't matter, right? So I can just reshuffle them. It's still the same thing because in a multiset there is no order. Much like in a set, there is no order here. Good. And to represent the multiset, we will usually use the uppercase X notation. So essentially, we're computing a local function, which is a function on the node representation itself, so on its own feature, plus the features that are in the multiset, which is given by the neighborhood, right? So two arguments here. two arguments. One is the node's own feature, and the other one is the multiset of neighboring features. And we are interested in a permutation invariant calculation, but this is guaranteed because we are acting on multisets, right? We don't impose any order, so this by construction is permutation invariant. And at the same time, of course, permutation equivariant. Good. So this, as I said, is a very introductory lecture to graphs. Before I conclude and before we go for the break, I would like to mention lastly that this is an instance of the geometric deep learning blueprint. Much like the deep sets, we are essentially dealing with a permutation group that's given by this multiset of neighbors, right? So this is defining the permutation group. And the functions that we are computing are essentially permutation invariant or equivariant functions respectively. Yeah, are there any questions about this? Yeah.
Can you clarify whether like the equivariance was in the case of nodes, but invariance in case of the graphs?
Sorry, can you say it a bit louder? I'm having difficulty in hearing.
There was equivariance, permutation equivariance in case of single nodes, but invariance is in case of the graph.
Right.
Can you distinguish between those? Like.
Right. So let's think of it this way. So let me find the slide to explain. So on a graph, what are we doing? So if we change the ordering, it's still the same object, right? So we don't impose any ordering. It's still the same object. What does that mean? My prediction, so the prediction that the machine learning model does, should be invariant to reordering or reindexing of the nodes, right? This is what it says for graph level tasks. When it comes to node level tasks, because my prediction is specific to a particular node, if I reorder, I still want the same prediction for that particular node, right? So the output has to be consistently permuted, just to make sure that, for node I, now it's not node I, but some I prime, right? I want this permutation to apply there as well. So this is what equivariance essentially tells me. So the same node should get essentially the same output. Does that make sense?
Does it mathematically also qualify as a equivariance in that case of node level tasks?
Yes. It's equivariance in that case, yeah.
One thing, we are presuming the same graph structure here, right? That we are modifying the edge matrix and the feature matrices. We're not morphing the graphs. If, say, we were to morph the graph, say, add or remove, like if look at a particular space of graphs, how would geometries, how would symmetries look there?
So in this context, you're right, we are not modifying the graphs, right? So we are not interested in modifications of graphs. This could be a different research direction, right? Here, what we're interested in is we have to represent the graphs in some way, right? And we want to make sure that when we make predictions over graphs, it should be invariant to these representational changes, right? So the choice of indexing of the adjacency matrix is arbitrary, right? So my prediction should not rely on that. That's what I would like to ensure here. Yeah.
I'm saying that if, say, we let's get a new problem statement where we want an architecture or we want a method that works across all graphs. So I'm allowed to modify a graph. Here I'm only allowed to modify an edge and a feature.
Well, modifying an edge is modifying a graph, right?
Adding new nodes. Adding, like, the node set is fixed here. The properties of the node set vary. And then I have 25 nodes. I will always have 25 nodes in this set, right?
Well, yeah, but so the graph you don't change, but this doesn't mean that you cannot apply to other graphs. So once you train your graph neural network, right, you can apply it to completely different graphs with different node sizes and so on.
The functions that we are using here, say we have one run of inference or one run of anything. I put in an input with 25 nodes.
Yeah.
My output will necessarily have 25 nodes.
Yes.
Let's relax that constraint. I can have 20 nodes, I can have 30 nodes. How would symmetries look then?
Oh, I mean, this we have to formalize this, right? We can't just, yeah. I mean, you're basically defining a setup without. Yeah, we have to formalize this to be able to talk about it, right? So you're saying the graph nodes may change during the, you know,
Function.
during this thing. So yeah, so basically that by definition doesn't respect any symmetry, right? Like we have to formally define what that means, and then maybe we can speak about it. But the way it's put, it just doesn't have anything to do with symmetries.
I think we can discuss that offline.
Yeah, yeah. 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 Thank you very much, and see you in the afternoon.